Good day everyone, I am Marquiza Sigaugay. For today's video, I'm gonna present to you the laboratory activity 4, which entitled Factors that Affect Solubility, the Nature of Solute and the Solvent. But before that, let me state first my objectives for this presentation. So first, to understand what solubility means. Second, to discuss the factors that affecting solubility. Third, to understand how temperature, pressure, and the presence of other solutes affect the solubility of solutes in solvents. So now, what is solubility? Solubility is the ability of a substance to dissolve quantity of a being soluble. A measure of this ability for a particular substance in a particular solvent equal to a quantity of a substance dissolving in a fixed quantity of solvent to form a saturated solution under specified temperature and pressure. So the first factor that's affecting solubility is the temperature. Basically, solubility increases with temperature. It is the case for the most of the solvents. The situation is though different for gases. With increase of the temperature, they become less soluble in each other in water, but more soluble in organic solvents. The second factor is the polarity. In most cases, solutes dissolve in solvents that have a similar polarity. Chemists use a popular aphorism to describe this feature of solutes and solvent, like dissolves like. Nonpolar solutes do not dissolve in polar solvent and the other way around. So third factor is the pressure. For solid and liquid solutes, for majority of solid and liquid solutes, pressure does not affect solubility. For the gas solutes, as for gases, the Henry's law states that solubility of gas is directly proportional to the pressure of this gas. This is mathematically presented as P is equal to Kc, where K is the temperature-dependent constant for a gas. A good proof of Henry's law can be observed when opening of a bottle of carbonated drink. When we decrease the pressure in the bottle, the gas that was dissolved in the drink bubbles out of it. And the fourth factor is the molecular size. The larger the molecules of the solute are, the larger is their molecular weight and their size. It is more difficult, it is for solvent molecules to surround bigger molecules. If all of the above mentioned factors are excluded, a general rule can be found that larger particles are generally less soluble. If the pressure and temperature are the same done out of two solutes of the same polarity, the one with smaller particles is usually more soluble. Stirring increases the speed of dissolving. Stirring does not have an effect on solubility of the substance, but everyone knows that he puts sugar in his tea and does not stir, it will not dissolve. Actually, if we leave the tea to stand for a long enough time, the sugar would dissolve. Stirring only increases the speed of this process. It increases move of the solvent, what exposes solute to fresh portions of it, thus enabling solubility. As molecules in liquid substances are in constant move, the process would take place anyway, but it would take more time. So now, let's proceed to the nature of solute and the solvent. So first, let's define first the solvent and the solute. So solvent is the substance in which solute dissolves to produce a homogeneous mixture, while the solute is the substance that dissolves in a solvent to produce a homogeneous mixture. Strong solute-solvent attractions equate to greater solubility, while weak solute-solvent attractions equate to lesser solubility. In turn, polar solutes tend to dissolve best in a polar solvent, while nonpolar solutes tend to dissolve best in nonpolar solvents.
The materials we're using today are alcohol, ink, cooking oil, gasoline, and water, and Zonrox, disinfectant Zonrox. And also we're going to use a dropper and 3 disposable cup as our container. And now the first procedure is that place 5 drops of cooking oil into each container. And after that, add 10 drops of water to the first container. For the second container, we're going to use an alcohol. And let's add 10 drops of alcohol into the second container. And for the third container, we'll be using a gasoline. And 10 drops of gasoline to the third container. And shake each container vigorously and record our observation.
So, my observation number 1, which is the cooking oil and water. Oil is less dense than water and floats on top of the water. Oil molecules, however, are nonpolar and they can form hydrogen bonds. The water molecules will bunch up together and the oil molecules will bunch up together, forming 2 distinct layers. And the observation number 2, which is the cooking oil and alcohol. Since oil floats on top of water, you might have thought that oil would float on top of the alcohol too. But the oil sinks to the bottom of the alcohol floats on top of the oil. Even though water and alcohol are both clear liquids, they have different densities. And observation number 3, which is the cooking oil and the gasoline. Gasoline contains many different nonpolar substances such as hexane, heptane, and octane. Therefore, gasoline effectively dissolves oils and even grease.
And the second procedure is that repeat procedure number 1, but replace cooking oil with Zonrox or disinfectant. Make sure that amount of disinfectant used are almost equal.
Observation number 1, which is disinfectant Zonrox and water. Zonrox mixed with water is an inexpensive and effective disinfectant. By mixing different amounts of bleach with water, you can make a high, intermediate, or low-level disinfectant when to be used cleaning up a large blood of a body fluid spill. Observation number 2, which is the Zonrox and alcohol. So mixing disinfectant Zonrox with alcohol dissolve well. Zonrox and rubbing alcohol creates chloroform. Observation number 3, disinfectant Zonrox and the gasoline. The observation is mixing gasoline with disinfectant Zonrox. I can say that it doesn't dissolve well. Bleach plus hydrogen peroxide creates oxygen gas too violently, it can cause an explosion.
Procedure number 3, repeat procedure number 2 but this time using ink.
Observation number 1, the ink and water. As water molecules move around randomly in a mixture with ink, they bump into ink molecules, causing them to move randomly as well. In places where there are more ink molecules, there are more collisions with water molecules that bump the ink molecules to other places. It dissolves well. Observation number 2, ink and the alcohol mix. They mix together well, which is another way of saying one easily dissolves the other. Permanent marker ink, however, does dissolve in alcohol, meaning the ink is dissoluble in it. Because of this, when you add the drops of alcohol to the design of the t-shirt, the ink should have spread out and run along the fabric with alcohol, creating a circle full of color. And the last observation, which is the ink and gasoline. The ink and gasoline doesn't dissolve well. They separate to each other. So for the generalization for this topic, solubility, the phenomenon of dissolution of solute and solvent to give homogeneous system, is one of the important parameters to achieve desired concentration of drug in systemic circulation for desired or anticipated pharmacological response. Strong solute solvent attractions equate to greater solubility, while weak solute solvent attractions equate to lesser solubility. In turns, polar solute tend to dissolve best in a polar solvent, while non-polar solutes tend to dissolve best in a non-polar solvent chelation. So for the continuation for this video, I will also discuss the laboratory activity 5, which is the factors affecting solubility and the pressure. And my objective is that to understand the factors affecting solubility and pressure. And there are two factors affecting solubility and pressure. So pressure affects solubility of gases. The effect of pressure are only significant in affecting the solubility of gases and liquids. Solids and liquids, the effects of pressure changes and the solubility of solids and liquids are negligible. The higher the pressure above of the liquid, the more gas that can be dissolved in that liquid. To a limit, of course, the solubility of gases depends on the pressure. An increase in pressure increases solubility, whereas a decrease in pressure decreases solubility.
And for this activity, we'll be using any carbonated drinks, but I choose Coca-Cola. First procedure, shake a bottle of carbonated soft drinks. Cautiously uncap the bottle. And then observe. The question is, when the soft drink bottle was uncapped, how did the change in pressure affect the solubility of the dissolved carbon dioxide?
And my observation is that the molecules of the carbon dioxides are thoroughly mixed and dissolved in the water in the soda pop. When you open a soda or a bottle, the carbon dioxide will begin to come out of the soda and into the water. Eventually enough will come out of the soda will become flat. Carbonated beverages contains carbon dioxide that has dissolved under pressure. When the pressure is released by opening the soda container, the liquid cannot hold as much carbon dioxide, so the excess bubbles out of the solution annually. And for the generalization, liquids and solids exhibit practically no change of solubility with changes in pressure. Gases, as might be expected, increase the solubility with an increase in pressure. The solubility of a gas in a liquid is directly proportional to the pressure of the gas above surface of the solution. An increases in pressure increases solubility, whereas a decrease in pressure decreases solubility. And that's all for today's video. Once again, I am Marquisa C. Gaugay. I hope you learned something and keep it. Thank you all and bye-bye.